As we review for the final exam, one of the important topics that we've covered and an important skill that you need from Calculus 1 is evaluating limits. Let's look at some of the practice problems and talk through some of the simple steps. And what my hope is that as you review this, you start to see, oh, is that all there is to it? It really is pretty simplified when you look at this simple set of steps. So I hope you'll jot these steps down and apply these with each limit that you're attempting to evaluate. Number one, here's the easy, low-hanging fruit. When you're out picking apples, you don't want to climb the ladder and do a lot of work if there's some apples hanging really low on the tree, right? Well, here it is. Try direct substitution. In many of these problems, you can simply replace the x in the expression with the constant and get no problems at all. And that's what we call an easy limit problem. But what's challenging about those easy limit evaluations is simply remembering to try direct substitution. What could you do to remember that every time? Start by trying direct substitution. The next step is to look at whether we have an x approaching a constant or an x approaching an infinity. And here's where we've got two different paths that we'll follow. Now, if x is approaching a constant and direct substitution gives us a problem, and that problem is usually a 0 in the denominator. So if direct substitution gives you a 0 in the denominator, try one of these two tools. Simplify either by factoring and reducing. And by the way, look at this little picture that I'm using. Do you see how I've written factor and then reduce kind of in the form of a fraction? That's to help you build a mental picture of a fraction, right? So when do you factor and reduce? When you have a fraction. And then when you have a radical, what you're going to usually do is multiply by a conjugate to simplify the radical. So again, when x is approaching a constant, we want to simplify the expression so that we can apply direct substitution. We typically can simplify the expression by factoring and reducing or by multiplying by a conjugate. And then that leads us to our other type of limit problems. So x is sometimes approaching a constant, but sometimes we've got x approaching infinity, either positive infinity or negative infinity. Here's the two different processes we use when we're evaluating a limit at infinity. A limit at infinity means a limit as x approaches infinity. Well, in the easy case is going to be the simple polynomial. Remember this really basic idea that if we're taking the limit of a polynomial as x approaches infinity, that limit as x approaches infinity is going to be equivalent to the limit as x approaches infinity of the lead term. So if we write that polynomial in descending order, then our lead term is the term that has the highest x exponent, the highest power of x. And the limit of that polynomial is going to be equivalent to the limit of that term. Really easy to apply that, and I'll show you some examples. Sometimes we have a rational expression, and do you remember this process? We're going to build 1 over x powers, 1 over a power of x, because the limit as x approaches infinity of 1 over x is equal to 0. And I can apply any power of x to this, 1 over x to the x squared. The limit as x approaches infinity of 1 over x squared is 0. The limit as x approaches infinity of 1 over x to the 5th is 0. So any power of x. So take a minute to think through these 3 simple steps, and let's try number 1 together. The first problem, number 1, is that polynomial. Well, first of all, let me say this if you didn't do this already. Did you notice what kind of limit it is? It's the limit as x approaches negative infinity. Number 2 is also x approaching an infinity. Specifically, it's negative infinity. So what we want to apply is either building those 1 over x to the something, or looking at this as a polynomial, which that's the case for this one. And we're just going to use that the limit of this polynomial is going to be equivalent to the limit of x cubed. The limit of the polynomial is equal to the limit of the lead term, which is x cubed. So we could simplify this limit to be the limit as x approaches negative infinity of x cubed. As we look at that, if we replaced the x with a negative number, a negative anything, it's going to turn out negative, right? And that's why it's a negative infinity. It's not that as x approaches negative infinity, we always get a negative infinity, because let me do a little diversion here and say, if we were doing this limit, if we were doing the limit as x approached negative infinity of x to the 4th power, anything to the 4th power, an even power, turns out positive, doesn't it? So this would equal positive infinity. So make sure, even though this particular example was an odd power, x cubed, make sure you could also do this if we had a x to the 4th. So don't just memorize an example. Instead, make sure you understand the example. Number 2, we also have x approaching negative infinity, but in this case, it's not a polynomial. So what we need to do is we need to build these little 1 over x to the n's. The way we do that is we look in the denominator and we find the lead term in the denominator is x squared. So the highest power of x is x squared. And that's why we're going to divide every term in the numerator and denominator by x squared. Why did we choose x squared? Once again, we looked in the denominator and picked the highest power of x, which was x squared. So we get 4x over x squared over x squared plus 4 over x squared. When we simplify that, we've got the limit as x approaches negative infinity. Oh, by the way, did you leave off this limit as x approaches negative infinity? I see that so often where students go from this step to this step and forget that it's a limit, and they just have this. Whoops, that's a mistake. Don't do that. Make sure you continue to write that limit. Oh, I know it's so much work writing limit as x approaches. I'm joking, right? It'll take you, what, 5 seconds to write that limit as x approaches negative infinity? Don't get lazy and leave that off, because when it comes down to it and you're doing a test or something important, you might forget that what you were doing was doing a limit. Okay, so what do we get for the limit as x approaches negative infinity of 4 over x? That's equal to 0. Oops, sorry, I'm erasing instead of highlighting. That's equal to 0. And what's the limit of 1 as x approaches negative infinity? It's 1. And the limit of 4 over x squared as x approaches negative infinity is 0. So we have a 0 over 1, which gives us a final answer of 0. The next example, we can divide by that highest power of x again. So the highest power of x in the denominator is the 2x squared, or not the highest power of x is 2. but the term is 2x squared. So I'm going to divide everything by 2x squared. When I do that, I get a 2x in the numerator. 2x squared over 2x squared is 1, and 1 over 2x squared is just 1 over 2x squared, I'm sorry. It doesn't simplify, right? So we get 2x. The limit of 2x as x approaches negative infinity is negative infinity. And then in the denominator, we no longer get a problem because we get a 1. So we could call this the opposite of infinity. We could call this negative infinity. Before we go on here, I noticed a little mistake I made, and I wanted to clear that up before we go any further. You may have caught this. What is 2x? Here it is right here. This 2x cubed divided by 2x squared. Those 2's divided out, didn't they? So I wouldn't have a 2 here. I would just have an x. I'll tell you why one reason why I think I made that error is usually what we would have actually divided by is not the 2x squared. We could have just divided by x squared. I've done that over here. You'll see that you get the same result, but I wanted to make sure that you notice that error. I hope that doesn't confuse anyone with that little 2 over 2 not reducing. Hopefully you caught that and saw it as we were going and were thinking, hey, I think that's a mistake. You were right if you noticed that, but notice that it doesn't change the outcome though. If I were to divide by x squared instead of 2x squared, that's when I'd get the 2x over 2 plus 1 over x squared, which still just gives us the negative infinity either way. Let's look at number 4. For number 4, we're going to divide all the terms by this square root of x squared. Now, when I write it in, it's going to be an x squared, not a square root of x squared when I write it in. But notice that the whole thing is in a square root, so be careful there. So we'll divide each term by the x squared, and that's going to give us 4 plus 2 over x squared over 3 plus 5 over x squared, and that whole thing square rooted. Again, don't get lazy. Don't forget to continue writing out that this is a limit. And then when I do that limit, we've got the square root of 4 over 3. Because what is the limit of 2x squared, 2 over x squared, as x approaches infinity? As x approaches infinity, that denominator gets to be huge, right? So we've got 2 over a huge number. And when we divide this huge number into this tiny little 2, we get a 0. So that limit as x approaches infinity of 2 over x squared is 0. The limit of 5 over x squared is also 0. So we're left just with that square root of 4 over 3. Continuing here in the second column, I could break that apart into the numerator and the denominator. I could break that square root up. The square root of 4 is 2, square root of 3 is just square root of 3. It's perfectly okay to leave your answer here with a radical in the denominator, but if you're really set on rationalizing that denominator, you'd also get that that's equivalent to 2 square root of 3 over 3. When we look at number 5, first off, we want to notice where is this limit taking us? It's a limit as x is approaching infinity. And for number 6, same thing, right? Do you remember what to do with a polynomial? Let me give you just a second to think about that. The limit of a polynomial as x approaches infinity, remember it's just the limit of that lead term. So this is going to be a quick, easy question. The limit of that polynomial is going to be the limit as x approaches infinity of negative, the opposite of x cubed. So the opposite of infinity cubed is the opposite of infinity or negative infinity. And then for number 6, when I replace the x with an infinity, we've got infinity to the 4th power. The answer is just infinity again. Number 7 and 8, we've got to divide the terms by the highest power of x in the denominator. For number 7, that's an x squared. For number 8, it's an x squared again. Try that division. Instead of just watching the video, pause the video for a moment and see if you can complete 7 and 8 on your own. Here it is worked out. When we divided by x squared, 3x to the 4th over x squared reduces to 3x squared. In the denominator, the x squareds divide out, and we got 3 left over. And then 4 over x squared, nothing reduces. When I do the limit, I get the limit in the denominator is going to be 3 plus 0, or just 3. Let me write that. So we have 3x squared. Let me make sure I'm clear here. So we have the limit of 3x squared over, if I do the limit, it's over 3 plus 0. So the limit of 3x squared is infinity, and when I divide infinity by 3, that 3 has no effect on the infinity. So it's just infinity. Number 8 is worked out here for you also, and I'll encourage you to somehow or other remember that negative stays out in front. And so our end answer is still a negative. For some students, it's writing it with a hot pink color or something else very bright. Other students will highlight it, but do something so that you don't lose that negative. Some students just excuse themselves and say, oh, I always drop negatives. Well, if you know you always drop negatives, come up with a strategy to take care of those negatives. As we move on to 9 and 10, notice that the limit is as the x approaches a constant for both of these, right? So treat it accordingly. If x approaches a constant and we attempt direct substitution first, you do find a problem. We get a 0 in that denominator. So remember what we're going to do. We're going to factor and reduce. X plus 3, and then when we factor this denominator, let me give you a little tip. This will not always happen, but often it will, that the problem gives us a little factoring tip. I knew when I went to factor the denominator that the only way I was going to get something to reduce was if I had a factor of x plus 3 in the denominator. So what did I do? Instead of trial and error again and again, I jumped straight to writing this x plus 3 in, and then I just had to think through, okay, what do I multiply this 3 times to get a negative 3? And well, the answer was negative 1. So I knew that that second factor was going to be x minus 1. Before I go on, I'm going to stop and check my factoring with FOIL. I'm going to stop and check that when I multiply first times first, outside times outside, inside times inside, last times last, I get the x squared plus 2x minus 3. And when you do that multiplication, you find out, yes, it does check out. So we get x plus 3 over x plus 3 divides out, and we're left with the limit as x approaches negative 3 of 1 over x minus 1. Now, once again, why did we have to go through this whole process of factoring and reducing? Here it is right here. We got a direct substitution, gave us a 0 in the denominator. Can you picture that little guy? Maybe it's you standing on, maybe he's standing on a log, or maybe he's standing on a unicycle, but he's yelling, help, I can't stand here, because you can't stand on a 0. Remember, you can't stand on a 0. So if direct substitution gives you a standing on a 0 in the denominator, you've got to do something, either using a conjugate or factoring and reducing to simplify. What's next when we get to this point? Do you see it? go back to direct substitution. We've solved the issue. We got rid of this problem with why we couldn't stand on a 0 because we got rid of, by dividing out, we got rid of what would give us a 0 in the denominator. So now with direct substitution, we continue this problem with no problem. So we apply a -3 here in the denominator and simplify and reduce. I'm going to leave that to you to finish. Number 10 gives us another 0 in the denominator. Help! He can't stand here because he's standing on a 0. It's like standing on a log or a unicycle. Or, I'm sorry, unicycle. What do we do next? We try to factor it. I'm going to give you a second to think through how to factor this x squared minus 2 or minus 4. The hint I'll give you is that it's the difference of squares. And I'm also going to encourage you to be mindful of this opposite sign out in front. So yeah, when we factor, don't forget this limit, right, that we're doing the limit as x approaches -2, and then don't forget that negative that's out in front. And once we do this factoring, we can reduce the x plus 2 over x plus 2, and we're left with the x minus 2. And then don't forget this negative out in front. Apply the direct substitution, and you should find a nice number with no trouble. Number 11 and 12, always, always, always start by trying direct substitution. Does it give us a 0 in the denominator or any other problem? Oh, look, they're so easy. 11 and 12 are so easy because all we have to do is replace the x with a 0 or replace the x with a -3. Oh, be careful. It's not -3 squared. It's not -9. If we have an x squared where x is equal to -3, it's the -3 squared. So here, this is like I'm writing it as the opposite of 3 squared. And this down here, what are we squaring? -3 is squared. So be careful about that our case is an opposite of 3, a -3 being squared. So -3 times -3 is +9. So make sure you're applying the exponent correctly. Number 13 and 14, try the direct substitution and see. Does it simplify right away? Oh, yay, number 13 does. Number 13 is an easy. You just apply direct substitution. Replace the x with a -2, and you're done. Number 14, not so easy. Oh, we've got a standing on that's not a very good face, sorry. We've got a standing on a 0. We get a 0 in the denominator, so we've got to come up with something else. Can you see what you could do to simplify that? It's called a complex fraction because we have a fraction within the fraction. To simplify a complex fraction, we could look for the common denominator, 1 plus x, and do something so that we can write this entire denominator, write the 1 over 1 plus x minus 1 all over 1 plus x. So we have to incorporate that -1 into the fraction. So we take that least common denominator, 1 plus x, and we turn that -1 into minus 1 plus x over 1 plus x. So then I could write it as 1 minus 1 plus x all over 1 plus x. 1 minus 1 minus x is going to leave us with an x in the numerator. Oh, I'm sorry, the x was already in the numerator, right? But down in the denominator, the numerator in the denominator, sorry, that's confusing. to say. I'm applying the arithmetic to this denominator, right? The x is no problem. This x in the top, let me highlight that x in the top. That x in the top, we just leave it. It just stays all the way through. But this denominator simplifies to the opposite of x over 1 plus x. How did I do that again? It was 1 minus 1 minus x. 1 minus 1, the 1 minus 1 just cancels out the ones. And then I'm left with minus x. So I get the opposite of x. And then we still have our denominator 1 plus x. The next step I did was I looked at this fraction as division. And remember that when we divide by a fraction, so we're dividing by this fraction, the opposite of x over 1 plus x, it's the same thing as multiplying by the flip, the reciprocal. So x divided by the opposite of x over 1 plus x is equivalent to x times the flip, the opposite of x under 1 plus x. When we do that simplification, the x's can divide out and reduce. This x and x reduce. Don't lose this negative down here, though. So we're left with 1 plus x in the numerator, and in the denominator, we have this negative. So it's the limit as x approaches -1 of the opposite of 1 plus x. And now using direct substitution, we get the opposite of 1 plus -1. And I'll leave that for you to finish as we finish the last example, number 15. Oh, darn. Too bad this last one couldn't have been a quick, easy one. But when I use direct substitution, I get a 1 minus 1, which is a 0 in the denominator. Can't stand on the 0, so we've got to simplify it. When I see a radical, what I'm going to do is use a conjugate. Now, the conjugate of the square root of x minus 1 is the square root of x plus 1. Why is that the conjugate? Well, what happens when I multiply two conjugates? It's like the opposite of factoring a difference of two squares. So I'm going to get this first thing squared minus the second thing squared when I multiply. And that square root of x squared is just going to be an x minus 1 squared, so minus 1. When I multiply the square root of x minus 1 times its conjugate, the square root of x plus 1, I will get x minus 1 in the numerator. So here's what it would look like. I can't just multiply the numerator by the conjugate. That wouldn't be fair. We've got to do it to the denominator also. So I'm going to multiply the top and bottom by the conjugate, square root of x plus 1. Again, when I multiply square root of x minus 1, let me highlight as I speak here. When I do this square root of x minus 1 times the square root of x plus 1, I get the square root of x squared, which is x, minus 1 squared, which is 1. In the denominator, oh, I'm not going to bother foiling that. Foiling it isn't going to help me, so I'm just going to keep it in its factored form. And you see what happens when I keep it in its factored form? Look at that. That x minus 1 over x minus 1 divides out into a 1 because x minus 1 over x minus 1 is 1. So now that I've factored it, I can simplify it. I can reduce it. And I'm left with the limit as x approaches 1 of 1 over square root of x plus 1. The last step, now that I've eliminated the issue, I've eliminated what gave us a 0 to stand on, which we couldn't stand on. But what gave us a 0 in the denominator is gone. So now I can just apply direct substitution. To apply direct substitution, I'm going to replace this x with a 1 and simplify. Well, that's it. I hope that this has helped you. Just recapping it again. Remember the simple steps. Number 1, try direct substitution. And then after you've tried direct substitution, pay attention to, is it x approaching a constant or is it x approaching an infinity? And if it's x approaching a constant, we're going to simplify. If it's a fraction, we're going to simplify by factoring and reducing. If there's a radical somewhere, we're going to use a conjugate to simplify. And then if it's x approaching an infinity, remember that the limit as x approaches infinity of a polynomial is just the limit as x approaches infinity of the lead term. If we've got something rational, then we can use the fact that the limit as x approaches infinity of 1 over x is equal to 0. And the way that we use that as a tool is we build the 1 over x to the whatever. We divide all the terms by the highest power of x that's in the denominator. Let me know if you need further assistance with this. Before we go, I'll flip to the answer key here in case you didn't see this. And you could pause to get a closer view of this. You know, you can do this. You can do these limits. If you want to be prepared for this on your own, what you need to do now that you've started with this video, what you need to do next is try to rework 1 through 15 without your notes. Try to work all the problems without any hints or tips and see if you can do it. What happens if you cut this paper, print the paper and cut it into 15 pieces and scramble them up and do them out of order? Can you get 100% every time? Or is there one of these examples that you struggle with? Look in your book or look online or talk to someone who can help you. Get some extra practice with any of the problems that you are still struggling with any of the types that you're struggling with. But what you've got to do is practice, practice, practice until you can get to 100%. If you play an instrument, a musical instrument, maybe you're used to that process. You learn something, you learn that piece of music, and then you have to go and you practice it and practice it and practice it. You sometimes don't practice the whole piece over and over, but instead go directly to that part of the music that you struggled with, right? And you practice that part again and again and again until you can do it perfectly. And then you go back to the start and try the 1 through 15 all over again and see if you can get to the point of getting 100% every time. You can do this. Math isn't just based on, well, how smart am I or how good am I at math? Forget that mentality. You're as good at math as you allow yourself to be. Practice, practice, practice. Work harder and you'll be amazed at how much easier it becomes.